Yeah, it's done.
Greetings from CSR List, Jorhat, Assam, India. I welcome all of you present online today. A very good morning to one and all present with us today in the day 7 of International Virtual Workshop on Global Seismology and Tectonics 2020. First of all, a big thanks to all the participants who attended the lecture by Professor Susan from USGS and Dr. RBS Jadhav from Kurukshetra University yesterday. Let's brace ourselves for another riveting session of knowledge sharing and integration today by Professor J.R. Kayal, who is going to deliver a talk on large intraplate earthquakes in India. But before that, may I request our session co-chairperson, Dr. Saurabh Barua, for his initial remarks. Over to Dr. Saurabh Barua.
Good morning, everyone present in this session. Today, we have with us Professor J.R. Kayal, who is a former Deputy Director General of Geological Survey of India, who is going to deliver about recent strong and large intraplate earthquakes in India. He is one of the doyen seismologists of Indian scenario and very much respected worldwide for his contribution. Whatever the earthquakes we know in India, is it strong or large earthquake, Professor Kayal is associated with that. He has taught GSI. All those earthquakes occurred during that time. Kilari earthquake, Jabalpur earthquake, Bhuj earthquake, and those earthquakes, not only as a seismologist, but as a strong geophysicist, he visited the field and looked after the all aftershocks recorded by his own hand with his entire team. And after the acquisition of the data, he has not only involved in field visits, entire database he and his team has analyzed and contributed in several ways to publish the research articles in various international reputed journals. So we are really honored that Professor Kayal is delivering his lecture today, and through his lecture we will be really enlightened, and our global participants will be really highly knowledgeable from this expert domain. So with that initial remark, I hand over the platform to Dr. Santanu Baru. Thank you, Shant.
Thank you very much, sir, for your initial remarks. Now let me read out a short biodata of Professor J.R. Kayal. Professor J.R. Kayal did his MSc in Applied Geophysics from the IIT ISM Dhanbad in the year 1969 and PhD in Microearthquake Seismology from the Victoria University of Wellington, New Zealand in the year 1983 as a Commonwealth scholar. After post-graduation, he joined the Oil and Natural Gas Commission, which is known as ONGC, in 1970. Then he joined the Geological Survey of India, GSI, in 1971. He rose to the rank of Deputy Director General in GSI and retired in November 2006. He has been as an emeritus scientist at the Jadavpur University, Kolkata, adjunct and visiting professor to various universities, institutes in India and abroad, guest faculty to the UNESCO and ICTP international training courses in South Asia. He is recipient of National Geoscience Award by Government of India, Lifetime Decennial Award by Indian Geophysics Union, and Fellow of West Bengal Science Technology. He has more than 140 research publications in national and international journals, authored a book on microearthquake seismology and seismotectonics of South Asia, and editor of several books and special volumes on earthquakes. He supervised more than 10 PhD scholars. He's an active researcher and student-loving professor in India and abroad. He's also the session chairperson of our international workshop on global seismology and tectonics. With this, may I request for most respected professor for his deliberation. About to Professor J.R. Kayal.
Thank you, Shantanu, for your very overwhelming introduction, and thank you, Saurabh, also for your very kind and so nice welcome address or remarks. I'm really feeling so good that this workshop is going so nice. I'm thoroughly enjoying it. I hope all participants are also enjoying it thoroughly. Today it is my turn to say something on recent strong and large intraplate earthquakes in India. Now, as Saurabh has rightly said, that my association with any strong or large earthquakes during my service tenure, I was present there to monitor aftershocks. So I'm going to share some of my experiences with you in understanding these earthquakes in India, in the intraplate region of India. Now, let me start from here. It shows that the Indian plate, which is moving to the north or northeast, some 71 million years ago, the position was somewhere here, and over the past million years, the Indian plate is now on head-on collision with the Eurasian plate, and the whole Himalaya has come up. So this is the present scenario, and with this collision interactions, the Himalaya has come up, and in northeast part of India, there was, in the geological past, there was subduction, but now it is also a collision zone or atypical subduction zone, you can say. The Indian plate is still dipping down to the Burmese plate over here, and that subduction zone or that Burmese arc is connected with the Andaman, Sumatra, Java subduction zone, and we are getting a lot of earthquakes along this subduction zone. So Indian plate, which is in between the 80° east latitude, there is a ridge, and at the 90° east latitude there is another ridge. Between these two ridges, 90° ridge and 80° ridge, the Indian plate is moving to the north or northeast, but the continental plate, but the oceanic plate is subducting along these trenches, along these Andaman, Sumatra, Java trenches, and this is connected also with the Burmese arc, the whole subduction zone from northeast to further southeast to Java. So that is the tectonic scenario. We are getting earthquakes for collision tectonics over here and subduction tectonics all over from northeast India to Andaman, Sumatra region. So in collision tectonics, Indian plate is moving to the north, and on head-on collision, the Indian plate is just gently going down or dipping below the Eurasian plate. And because of this head-on collision, the Himalaya has come up, and we are getting a lot of earthquakes in the Himalayan region. Of course, this is a pictorial view, not exactly of the Sumatra trench, but you can see how the oceanic plate subducts below a trench, and then how that subducted plate gets melted and comes out as a volcano along the volcanic arc. So at a subduction zone, you have a trench, you have a dipping subducting plate, and on the surface you have a volcanic arc, and all along the subducted plate you have earthquakes. Let us see over here the seismicity in the collision zone. As you can see, this is the western syntaxis zone, and this is the eastern syntaxis zone. So about 2,500 km long Himalayan belt with intense seismicity due to this collision tectonics. And in the Indo-Burma ranges, we also get a lot of earthquakes, which is connected with the Andaman Sumatra subduction zone. This is Andaman Sea Ridge. And these earthquakes are all due to subduction tectonics. Now over here also you can see that this is the spreading zone, the Carlsbad spreading ridge. And the spreading zone also generates some earthquakes due to tensional stresses. Those earthquakes are between magnitude 4 to 6. They are not large earthquakes, but we are getting large earthquakes or great earthquakes in the Himalayan zone and also in the subduction zone. And as you know, the Sumatra 2004 mega earthquake. Now these sections were published by Rao and Chari. They found that if we take the sections of the earthquakes across Indo-Burma ranges, then it shows that the Indian continental plate is down to about 200 kilometers or so. There is a seismic zone or Benioff zone, and there is overriding plate earthquakes in the Burmese plate and Indian intraplate earthquakes over here, and this Indian plate is subducting below Indo-Burma ranges. Now, across Andaman zone, you can see that subduction is further deeper, and this is Handa plate earthquakes, overriding plate earthquakes, and this is subductive plate earthquakes. As you come to Sumatra, this dipping seismic zone is further down to about 450 or 500 kilometers, and as you go to Java, the subduction zone down to 660 kilometer depth, all along this Benioff zone or seismic zone. Now, 2 days ago, Walter has shown that this is not this textbook type of subduction zone over in the Java trench. If you go further east, the subduction tectonics is more complicated, and there are also ocean-ocean subduction, double dipping subduction, and the subduction zone is also, there is a gap between, say, between 200 to something like 500 kilometer depth. There is no earthquake, then there is a deeper earthquake zone. So all sort of complication starts in the further east of Java island, but this work shows how nicely this subduction zone from Indo-Burma ranges down south as it goes to Sumatra, Andaman, Sumatra, and maybe west of Java, how it is textbook type of subduction zone, and I think this is one of the deepest subduction zone in the earth. So I think this is this much, and we are today not talking about the Himalayan earthquakes or Indo-Burma range earthquakes or these subduction zone earthquakes. Today we will concentrate our earthquakes only in the intraplate region, and as you can see, there are some intraplate earthquakes over here. That is Koina, that is Kilari here, there is some earthquake here, Jabalpur. Then this is the Western India, the Bhuj area. There is also a large earthquake over here. So we will talk about those earthquakes, intraplate earthquakes today in this presentation. We will try to understand these intraplate earthquakes. Now, if you see the large earthquake scenario, magnitude 7 and above, the stars are showing great earthquakes: 1950, 1897 Shillong, 1934 Bihar, Nepal, 2005 Kangra, then 1905 Kangra, then somewhere here 2005 that large earthquake in Kashmir. So all along the Himalaya we have got great earthquakes, though the Shillong earthquake is no more considered as Himalayan earthquakes. It is an intraplate great earthquake, and this part of the country is lot of large earthquakes and 2 great earthquakes. So I will not, though it is an intraplate earthquake, I will not touch upon this intraplate earthquake in Northeast India, because there is a separate lecture on Northeast India by Dr. Saurabh Barua, and maybe today evening, so we'll listen to him. So I will just concentrate to the large intraplate earthquakes in this part of the peninsular India. That is, again, this earthquake, Koina earthquake, is an intraplate earthquake, but it's a different story. So altogether, it's a field laboratory for NGRI, and I think thousands of papers are published on this earthquake. This is the a great example of reservoir trigger seismicity over here. So I will also not talk about this earthquake. This occurred in 1967, Koina earthquake. I will just concentrate on our presentation today on the Kayal earthquake, what we learned about Kayal earthquake, which occurred at the middle of the Indian plate over here, center of the India. Then some earthquake over here, that is 1997 Jabalpur earthquake in this zone. Then there was another earthquake, large earthquake, Bhuj earthquake in 2001. There are some more earthquakes in this region, that is 1819 great earthquake. I will also not talk about that. And there are also one strong earthquake in Western India, that's called Anjar earthquake. So we will concentrate on Bhuj earthquake, Jabalpur earthquake, and Kayal earthquake, what we understand from the aftershock study. Now, as I said some other time that seismology is a young science, and particularly it is, I think, in India. In case of India, it is still younger, in a sense that we had first observatory after the 1897 Shillong Great Earthquake that was established in Calcutta in 1998 December. And during 1989, two more stations came, one at Colaba and one at Kodaikanal. Then after the 1905 Kangra earthquake, great earthquake, three more observatories, and over the years, say by 1960, some 15 observatory came in the national network. It was all under the auspices of India Meteorological Department. It is still under that department, but a separate department has now come up. Now, since 1996, the broadband observatory or network has been established in India. That also happened after the 1993 Kayal earthquake. That was the earthquake which shook the whole world actually. The whole world came to see what has happened. That was a catastrophic destruction and damage and loss of lives by that earthquake. Such a sudden earthquake in the center of the Indian plate. So there is some stuck, I don't know why. I hope the connection is all right. Hope it will work all right. Now let me talk. So we'll see what happened with the Kayal and Jabalpur and Bhuj earthquake. I hope my slide works.
It is not moving.
Sir, please unmute your microphone.
Sorry. So this network has started in 1996, a broadband network after the 1993 earthquake, and it was not moving. Let me see whether it moves. Not moving from here. Yeah. Okay. I think due to slow in my computer system, sometimes I get stuck. So I think it will be all right by now. Now, before I go to the actual examples of the aftershock investigation of the Kilari, Jabalpur and Bhuj, let me give you some glimpse of basic knowledge of earthquake location and seismic tomography and fault plane solutions. Because since it's a workshop, it's not a seminar lecture, so I will give you some glimpse because I cannot take up fully due to time constraint, but just what we do, what the seismologists do. We record the earthquakes, say in the field, in the analog mode, it is like this. In the smoke paper record looks like this. This is P wave and this is S wave. And in a digital system now, we are recording 3 components of the seismograms, and they are very nicely, they can be read, and S wave particularly can be very well read from the vertical, from the horizontal component of the seismogram. So now our basic data is arrival of P time and arrival of S time. That is the basic data for earthquake location. But before the computational method came, say before 1950s or 1960s, the earthquakes were located by manual method. That is, if you know the S minus P time, the interval of S time and P time, that S minus P, this interval approximately gives 8 times of that interval is the hypocentral distance. This distance is about 8 times the S minus P time. Say 8 is the S minus P time. Say or 10 seconds the S minus P time. Then about 80 kilometer is your D. So that gives an approximate hypocentral distance of an earthquake from the S minus interval. So if we have 3-4 stations and you have interval time, say 10 seconds, 12 seconds, 15 seconds, like that, so you can draw arc on the map, and that intersection can give you the epicenter. So that is how the earthquake epicenter used to be located manually before the computational method came. And if you know the epicenter distance, now you can find out the the hypocentral distance, so you can find out the depth. So that was how manually epicenter and depth was estimated before the computational method came. But when the computational method came, then the earthquakes are located by least square method. Now in least square method, the most popular computer program is Hypo71 and Session. By this, we try to do the multiple regression to locate the earthquakes with a known velocity model. Then when the more advanced technique like joint hypocenter or double difference or tomography came, a researcher was trying to do best of the data, to make use of best of the data, and they could do the better location by master event method. These details are given in my book, you can see that. Or by average residual method, means you are taking the average residual of a station as is station correction, or you are taking a master event and which is well recorded and taking the station residuals as your station correction. And the best one was, to me, is the homogeneous station method. Means you are locating earthquakes with same station set with same phase data also. Means say for at station A you have P and S, at station B you have P and S, like that. So you are using a particular station set with similar phase data, same phase data. That means homogeneously you're trying to locate the earthquakes, and that used to that method is to give a much precise location in a sense that was independent of the, if there is a random error, that could be minimized by homogeneous method. There will be error, but it will be systematic error. So that way, homogeneous method was giving a better locations. But when the computational technology is further advanced, then came the joint hypocenter method, determination method, JSD. That is, you also estimate the station correction and incorporate it with your location, because your all stations are not, on the same geologic formation. Some are on the alluvium, some are on the hard rock. So station to station, there is a delay time, or some rays are very fast at some stations due to the hard rock condition. So the station correction is used to be computed by this method, and then double difference means, suppose your two earthquakes are very close to each other, and you can take the difference of this, arrival time and compute their comparative, location of the earthquake. So that is called double difference method. Then comes the simultaneous inversion method, means you locate the earthquakes, epicenter of the earthquakes. You locate the earthquakes at the same time. You also, by simultaneous inversion, you also develop the velocity model. You also find out the velocity model, the 3D structure of the velocity. Say, for example, this Pacific plate is subducting below Japan Trench. So this is the high velocity Pacific, subducting plate, and the blue is high velocity perturbation, and this red is low velocity, lower velocity. So below the volcanic arc or the overriding plate, there is a heterogeneous low velocity structure. So this is how you can image the structure below the earth, and you can also relocate the earthquakes more precisely, incorporating this heterogeneous structure below your network. So this is how the different method works. Now, what about magnitude? Now, as you know, the most popular magnitude is Richter magnitude. Is 1935. He first designed the magnitude scale, and the magnitude and intensity are two different things. They are always confused by the journalist. The magnitude is the, it gives the measure of the energy of the earthquakes, how much energy is there. Say, for example, at a magnitude 8 earthquake has some 1 million atom bombs energy of Hiroshima type. So the magnitude is to give an idea, or get an idea about the energy of that earthquake, how strong that. A magnitude 8 is about, the magnitude also goes in power scale. So a magnitude 8 earthquake is equivalent to about 33 earthquakes of magnitude 7 at a time. So similarly, the say 9 magnitude earthquake of Sumatra subduction zone, that is equivalent to about 33 magnitude 8 earthquakes at a time. So that is the power scale in magnitude scale, and how it goes, the energy, how it increases in a power law. But intensity is totally different. Now, by the way, over the years till today, I think it is still a very popular scale, but it has got a limitations. And this scale was designed by Richter. He assumed a very wonderful nomogram he developed. He assumed that if an earthquake is recorded with 1 millimeter amplitude by Wood-Anderson seismograph, and that earthquake say occur at a distance of 100 kilometers, then that earthquake magnitude is 3. So an earthquake at a distance of 100 kilometers recorded with 1 millimeter amplitude by Wood-Anderson seismograph is assumed of magnitude 3 earthquake. So based on that assumption, he designed this nomogram. So this side is your S minus P time scale or distance, and this side is the amplitude. So maximum amplitude you can read, and S minus P time you can read. So S minus P time you say about 24 seconds here, so you mark it here, and maximum amplitude you say 23 millimeter, so mark it here, and you join these 2 points, you get the magnitude. This is the magnitude scale. So this scale works so well, it's so popular scale, and now, of course, different magnitude scale has come based on the digital seismograms, and Richter magnitude also gets saturated, say at 6.5 or magnitude 7 above the Richter scale saturated. So maybe magnitude MW works very well, but we have surface wave magnitude, we have body wave magnitude, we have duration of the signal you can take and get a magnitude. And we can also, from the damage survey, you can also empirically develop an equation to find out, to estimate magnitude, because say for the past earthquakes, you have no instrumental record. So for those earthquakes, magnitude can be estimated from the past, damage report. So like that scale, it is the degree of damage, and it varies from place to place. As you know, intensity at the epicenter area is maximum, and as you go away, intensity. Now there were initial scale was by Rossi Forel, the intensity scale. Then it was modified by Mercalli, and it was called modified Mercalli scale. It is also very popular scale like that of Richter scale in magnitude scale. And then a new scale has come. It's called MSK scale. It has come from 1992. Now people are more fascinated to do damage survey using this MSK scale. Like we are now mostly using MW for estimating magnitude. Similarly, MSK for intensity. I think that's that much. I think I wanted to tell you. Now, what seismologists try to understand location, magnitude. Having done this, they try to understand what type of faulting has causes these earthquakes. So there are two types of fault plane solutions. Two methods are there. This classical method is fast motion solution, and with the digital seismogram, we can also estimate. We can also find out the moment tensor solution. The basic principle, of course, the same. That comes from elastic rebound theory, Reed's elastic rebound theory. And it is based on this theory is based on the practical example of the 1906 San Francisco earthquake. There was the ground motion was visible. There was a fault, and the ground moved by some 3, 4, or 5 meter separation. So based on that practical observation, this theory was developed, and it gives that if there is a fault and there is a ground motion like this, then we can and if we imagine an orthogonal plane, then you can get some, due to this type of ground motion, you will get dilatation motion in this quadrant and up motion or compressional motion of the ground. If your instrument is here, it will record up motion of the P wave, fast wave. So that was the concept was taken from this elastic rebound theory, and it was developed to plot this fast motion by geological method. You call it stereographic net on which we can plot. Suppose this is your earthquake at depth, and that on the map it is epicenter, and this is your station. So the station's azimuth and the angle of ray path, these are all computed when we do the earthquake location by computational method. So when you know the azimuth and you know the angle of incidence of the ray path, you can plot them on a stereo net, and you can plot the compressional plot and the directional motion plot, and you can separate them with two orthogonal planes. And the dynamics of the faulting is like this. When your compressional stress is dominant and horizontal, you get thrust faulting, and this is how we represent them. When your tensional stress is dominant and horizontal, you come out with a normal faulting, and this is the beach ball representation. And when your both compressional stress P axis and T axis tensional stress are horizontal, and the intermediate stress is vertical, then we come out with a strike slip solution. So these are the beach balls that what we get from this type of plot, stereo net plot. And suppose this is a pure thrust faulting solution, and this is also thrust faulting with some strike slip component, and this is strike slip, almost pure strike slip mechanism, and this is normal faulting mechanism. So, and this has got normal faulting with some strike slip component. So these beach balls I will show in my coming slides. So now we just try to remember that seismologists try to do the fault plane solutions based on fast motion data or based on the waveform inversion. This is an example from the IIT ISM observatory. Here what we do, the actual observed seismograms, we try to make synthetic seismogram, assuming its focal depth and the solutions, and the best match is taken, and this was the strike slip solution for this earthquake at the ISM observatory. So also by waveform inversion, you come with a fault plane solutions, and the basic classical hypothesis I told you how we try to understand this. Now out of these two nodal plane, one is fault plane. So as I said, this is fault plane and this is an orthogonal plane. So between, if you know this is fault plane, it's fine. But if you do not know which is the fault plane, then you have to judge which is the fault plane. Is out of these two orthogonal plane that you are separating. Say here also you are separating by two orthogonal planes, compressional zone and the directional zone. Then out of these two orthogonal plane, one is fault plane, and how we interpret that I will show you with the examples. Now, this shows that how the intraplate earthquakes behave in the Indian plate. You see, we have got Koyna earthquake, 1967 Koyna earthquake, I think one of the earliest earthquake, intraplate earthquake in Koyna, and this is in the center of the Indian plate. This happens that that Kilari earthquake. This is also you can see. The Koyna earthquake is by strike slip faulting, whereas the Kilari earthquake is by thrust faulting or reverse faulting. Reverse faulting is when your dipping plane is more than 45 degrees, we call that thrust faulting as reverse faulting. So your Kilari earthquake is now, you can see it's thrust faulting, and your Bhadrachalam and Ingol earthquake were by strike slip faulting. The Midnapur earthquake was by almost thrust faulting with some strike slip component. Then this one is the Bhuj earthquake, and this one is the Broch earthquake over here. So they are all mostly by reverse faulting and strike slip component. There's another earthquake over here, Anjar earthquake. This is by pure thrust faulting. So now you understand these different beach balls, strike slip and pure thrust. So these beach balls, we'll see how we understand with the actual examples. Now I am coming to our focused three aspects. Now let us try to understand this 1993 Kilari earthquake. This earthquake occurred somewhere here in the center, in the Deccan, covered area over here, and there were some Tirna river is flowing like this, and one tributary is flowing like this. But there is no other surface fault mapped in this region because it is a Deccan covered area. So there is no clue which is the fault and on what fault this earthquake occurred. So as we, immediately after the earthquake, from GSI, we took a team and made a network around the epicenter area and very close station network, so that this earthquake was only at a depth of 7 kilometer depth. And we made a very close station network, something like 10-12 kilometers away. There are some 8 or 10 stations we put around the main shock, and this was the effect of the main shock. You can see that the total damage, the whole village was destroyed. Actually, these villages are the houses are made of big boulders with mud, as a cementing material. So when the earthquake occurred, the ground setting, the boulders were collapsed and the people are killed by the boulders. And it was a very early morning time, so people are all in the, all are in asleep. But you can see that a house far away is standing. So that means the well-built house survived, but the poor houses made of boulder and mud, they all totally collapsed, and there are some 10,000 plus casualties by this earthquake. You can see here one engineering structure, I think some water tank that survived. There is some little damage, but that survived well, and also other houses survived. Now, this earthquake had little bit evidence of surface rupture. In patches, it was about a kilometer long surface rupture was observed by this, by this earthquake. It was a shallow earthquake at a depth of 7 kilometers, so there was surface rupture was visible, but not long, about a kilometer. Now, this is our stations and this is our aftershocks. Now, this is the main shock solution. And now you understand this is the fast faulting or reverse faulting, and this is the solution for the for the aftershocks, deeper aftershocks, and for the shallower aftershocks, this is the fault plane solution. So this is a strike slip solution, or normal faulting dominated strike slip solution. This is thrust fault solution, and this is also a thrust fault or reverse fault solution of the main shock. Now, to examine if there is no fault mapped, so we try to understand this cross section of the aftershocks. These are very well located earthquakes by simultaneous inversion, by seismic tomography. So I'll come to that. Now, when we take the north-south section of these earthquakes, this is south, this is north. The aftershock shows a dipping structure. Main shock is somewhere here, star mark, and all deeper aftershocks has shown a quite a dipping plane like this, and the shallower aftershocks means 0 to say 5 kilometer or less. Those aftershocks are on both sides of this dipping plane, but the main shock and the deeper aftershocks are showing a dipping plane, and this dipping plane is south dipping plane, and this dipping plane also, when we extrapolate it, it matches with the surface rupture over here. So this is the dipping plane or fault plane we presume could be the seismogenic fault. And if you see the fault plane solution, you see this nodal plane, which is south dipping, is also matching with this south dipping, aftershock section. So our interpretation is that this solution shows that this south dipping nodal plane is the fault plane, and that is the fault plane. And for the the deeper aftershocks also show thrust faulting. So main shock and deeper aftershocks almost similar solution, but the shallower aftershocks over here, 0 to 5 kilometer depth, we find their tri-slab movement. So we tried to make a model how it can happen. So there is a fault interaction model we have tried to make. So the upper block, which is about say 0 to 5 kilometer depth, that upper block overthrusted, and that caused the main shock, and the upper block itself moved by strike slip mechanism and generated shallower aftershocks. So that was our understanding, that a fault interaction model, upper part by strike slip movement, and the lower part there was a thrust movement or reverse faulting movement. Having understood this, we try to do the tomography of this. In this, we had something 160 good, earthquakes, well located earthquakes recorded by some 8 or 10 stations. So those data we took, this is published in BSSA. You can see the details, or also in my book. Also you can see. So at a depth of 6 kilometers, means the earthquake almost at a hypothetical depth, we find this is not color. That time we had only this black and white picture could be published. So this you can see this one, the lower velocity structure, east-west structure over here. There is of course another structure here, but this structure and this high velocity structure, this dark part. So this is at the contact of the low velocity and the high velocity structure, that heterogeneous linear structure, the main shock, the star, this main shock occur. And at a depth of 3 kilometers, we find there is a one low velocity structure along this northwest direction, and which is very much matching with the geomorphologically with the Tirna tributary. And this east-west fault structure is matching with the east-west Tirna river. There is a river over here, and that geomorphological evidences indicate that that could be a east-west fault, and that is imaged by this tomography structure here. Actually, I have a good experience of this publication. When I sent this paper to BSSA, one reviewer from USGS, it was recommended immediate publication, and he remarked that it's a textbook type of seismic tomograms, and it should be published at the earliest. So that is how, without revision, that paper was published in BSSA in 2003, and we were very happy with this observation and this understanding of this earthquake, Kayal earthquake. Now let us come to the Jabalpur earthquake. The Jabalpur earthquake, if you see this map, this is the Narmada, rift basin, and this rift basin about 1,000 kilometers long and about 50 kilometers wide. A rift basin means due to the Indian plate movement, there is a rift, in the middle of the plate, and so that rift basin is called Narmada rift basin. And in this rift basin, there are some past earthquakes, like Damu earthquake, 1846. That time there was no instrument, or this magnitude was not estimated. Intensity, past record shows the past, SOs observation shows the intensity could have been up to 8. And there was a Son Valley earthquake in 1927, that is over here. This is 1846. This is 1927, Son Valley earthquake 6.5, and Satpura earthquake 1938, magnitude 6.0, that is somewhere here. And this Jabalpur earthquake 1997 is this one. This one is Jabalpur earthquake, and this is the mechanism of that Jabalpur earthquake by USGS or so. So, and that earthquake, if you see the damage, one house, the first floor totally collapsed, and these poor houses also totally collapsed, and this fairly well-built temple, there is some crack. So we actually work in two teams. One geophysics teams, they go for aftershock investigation, and one geology team, a big team of geologists come for macroseismic investigation, for intensity or for isoseismal mapping. So the intensity map was given. I forgot to tell you, the Kayal earthquake intensity was also maximum, it was 8. And for this earthquake also, we reported maximum intensity is 8. This is that oval zone intensity 8. And we first, seeing the epicenter here, we first install our stations over here, then we put some more stations to the southern side to have a better coverage. And you can see that all the aftershocks there are not many aftershocks. I will tell you why. So all the aftershocks are, on this side of the other side of the. In Kayal case, all aftershocks are within maximum intensity, but in Jabalpur case, the aftershocks are all outside, maximum intensity. So that was an observation. And this is main shock, the star shows main shock, and this is possibly IMD solution, this is possibly CMD solution, and this is our solution of the aftershocks solutions, fault plane solutions. Now, when we took the sections of these earthquakes, it looks like this. Now, here I have a point to make that during this macroseismic survey, the geologist identified one fault on the in Jabalpur area, and they named it fault FF, which is within the system of Narmada South fault. So this fault of the maximum intensity on the other side of the fault, and the aftershocks and main shock on the other side of the fault. On the hanging wall side, the aftershocks and the main shocks, and on the footwall side, there was maximum intensity. That is very some interesting observation. Now, this section is given from DSS section, Now there was a DSS profile across this, Narmada Reef Basin, and that DSS profile, I think, is not much visible. But I tell you, the Narmada North Fault is identified, Narmada South Fault is identified, but this fault FF dot, which is this fault, it was missed by DSS sounding. This is the fault which was mapped by the geologist, and this is the fault which we also get from our aftershock cross section. And aftershocks are all, you can say downwards at the crust mantle boundary. This earthquake occurred, the main shock. And by the way, this is the first strong earthquakes, or first earthquake which was recorded by all. That time we think we had something like 10 or 15 broadband stations by 1996. By the broadband stations, this earthquake was recorded. The first earthquake recorded by broadband network, and its depth was very well estimated. Depth was 35 kilometers, and aftershocks are also between 35 to 47 kilometers, all at the crust mantle boundary. These aftershocks, and this is the main shock. The rupture goes down the downward direction, and only some, I think, 40 or 35, 37 aftershocks we recorded. So we could not do any seismic tomography with this very meager data, but we could do the sections, and we could do the fault plane solutions, and from there we interpreted that some south dipping fault, FF fault, was the positive fault, and at the fault end, at the crust mantle boundary, that main shock occurred. Again, I am stuck. Sometimes my is very slow. Yes, no, I am not come. The system has become slow. It takes some time. System is so slow. I'm nearly done. Another 2-3 slides for Bhuj earthquake I'll show you.
So can you take some questions to save our time?
You can ask some questions.
Yeah, Sir Prasidjo.
Yes, please.
Unmute. Prasidjo, please unmute. Prasidjo, please unmute your.
Yeah, sorry, sir. Okay, the first question is, does Intraplate earthquake has the potential to generate an earthquake of magnitude more than 7.5 magnitude? If it is possible, what will be the fault typing? And in India, which Intraplate fault has that potential?
Yeah, very good question. Yes. Say in the typical Intraplate region, say you can say the typical Intraplate earthquake is a Kayal earthquake, which is very shallow and magnitude 6 or 6.3. And the two other earthquakes that we have already, one is discussed, the Jabalpur and Bhuj. They are Rift Basin earthquake. They are deeper earthquakes. The Jabalpur earthquake was at a depth of 35 kilometers, and Bhuj earthquake was at a depth of 25 kilometers. So among all these source zone, say typical Intraplate zone, we do not expect or 6.5. Say Pune earthquake, that was the maximum magnitude, or say Kayal earthquake magnitude 6.3. These are typical intraplate region, but in the Rift Basin, particularly in the Bhuj Rift Basin, we have earthquake of magnitude 7.8 or 7.7. So I would imagine that in the intraplate region, only the Kutch region is capable of, it has already produced 1819 large earthquake, which produced something like 90-kilometer long, they call it Allah bomb, a long wall, crustal deformation of 1 meter height. So the 1819 earthquake is a large earthquake, and the 2001 earthquake is also a large earthquake. So the Bhuj or the Kutch Rift Basin is capable of, already we have experienced 2 large earthquakes, is capable of producing large earthquakes of the order of magnitude 7.5 plus. So far the Jabalpur or the Narmada Rift Basin is concerned, we have the past earthquakes 6.3, 6.0 and 6. That I think that we have recorded 6.3 or so. So in the Narmada Rift Basin, though the fault is a long fault is there, but it's not a continuous fault, it's a fault system. So not that all along the fault is active and it is generating earthquakes. So there are some asperity zones, some locked part and some unlocked part. So in the Narmada Rift Basin, I would expect that earthquakes of magnitude 6.5, and for any practical power plant or anything, for any design, we always take another 0.5 plus. So yes, so my response to you, the question is, in the typical intraplate region like that of Koyna or like that of Kilari, where we get shallow earthquakes and typical intraplate earthquakes, they would be of the order of magnitude 6 to 6.5. In Narmada Rift Basin also, it could go up to magnitude 7, but magnitude 6.5 is the highest magnitude recorded. And Kutch Rift Basin, which is also an intraplate zone, which is capable of producing large earthquakes, as we have already seen, that Rift Basin is capable of generating earthquakes magnitude 7.5 plus another 0.5, say 7.5 to 7.9 or 8, up to 8, because 1819 earthquake was estimated magnitude initially was 8.0 or 8.1, and a revised magnitude 7.8. So yes, that is the scenario. And as you see in Bhadrachalam or Ingol, the magnitude is of the order of 5.3 or 5.4, and also in the Singhbhum area or in Midnapur area, the recorded magnitude is of the order of 5.3, 5.4. So that is the scenario in Indian intraplate region. I think I could reply to your question.
Yes, sir.
So please take your slides. Sir, please take your slide. Whether it is moving or not. Sir. If it is not moving, then we can go for second question. Procedure.
Yes, sir. Should I proceed for the next question, sir?
Yes, please.
Yes, please go ahead.
Okay, sir. Ashish Paul wants to know, in focal mechanism, why do compressional fields define T-axis and dilatational fields P-axis?
Ask the question again.
In focal mechanism, why do compressional field defines T-axis and dilatational fields P-axis?
Okay, if I can go back, I am not able to going back. Now let me explain you this way. Look, the technique says that your intersection of the two nodal plane is the position of intermediate axis, that the B axis. Okay. Now, from the intermediate axis, that is from that intersection, you draw another circle with the help of stereo net, and on that 90-degree arc lies your P axis and T axis, that is compressional stress axis and tensional stress axis. And in that plot you will see that T axis comes in the middle of the directional zone, and P axis come in the middle of the compression. In the T axis come in the middle of the compressional zone, means where there is a dark part of the beach ball. The T axis come there, and the P axis comes in your directional zone. So that is how the stress axis has to be all orthogonal axes. So they have to be at 90 degrees with each other. So once you find the intermediate stress axis, that is the intersection of the two nodal planes, then that 90-degree arc, again they are also at orthogonal situation, means P and T also at a orthogonal situation. So they will be also separated by 90 degree. So that way we come out with the compressional P axis in the directional zone and T axis in the compressional zone.
Okay, sir. The next question is, how liquefaction would work in different magnitude earthquake in alluvium, and how to identify such places?
Sir, your voice is not clear, sir.
Okay, could you please repeat again? Could you please repeat?
Yes, sir.
Yeah.
How liquefaction would work in different magnitude earthquakes in alluvium, and how to identify such places?
Oh, I think it was well explained by Susan yesterday night. If you have attended that class, that lecture, she was wonderful. The first condition is that it has to be loose soil or loose sand or whatever, and the second condition is that water table is very shallow. So where there is shallow water table and loose formations, loose sand or whatever, then that water comes due to the shaking. The water comes to the surface where and the loose sand gets liquefied. So that is, I think, very quite understandable. So it has to be shallow water, and if the ground shaking is much, naturally the water comes up and it liquefies the loose soil. Yes. Any other next question?
Yes,
I will just see if I can fix. Yes, just 1 second.
Okay.
Yes, could you please tell? Yes, next question, please.
Sure, sir.
Yes.
K.N. Prasad wants to know, does the magnetic material from the reunion hotspot along the Narmada Tapti rift system could be one of the reasons for seismicity in the central India?
Yes, another good question. Actually, we could not do seismic tomography in the Narmada Rift Basin due to very meager data, but we could do seismic tomography in the Kutch Rift Basin, and in the western part of the country, in the below Kutch Rift Basin, by global tomography, it was seen that below Kutch Rift Basin there is a very low velocity zone there. So there is existence of magma, and also this local tomography by our Kutch, Bhuj aftershocks also shows that the low velocity structure just at the mantle depth or so. So okay, I think I have come. I have come with the.
Sir, please unmute your microphone.
Yes, I think the low velocity zone have been identified below Karst Basin, and that is one of the reasons. That is not the reasons that actually accentuate the earthquake, that helps the triggering of the earthquake. Now, the main cause of the earthquake is the tectonic stress. Now, let me complete the lecture. I think I will take another 5-7 minutes to complete it. Please let me complete fast. Then, if you come to the Bhuj earthquake, this is my last, last earthquake to share my experiences. Now, this is a very complicated zone. You can see that Northern Basin, that Canberra Basin, the Western Coast Fault, then the Kutch Basin, all are in this zone. And this zone has, this Canberra zone has got a Mount Abu earthquake. Then this Narmada, this is Broch earthquake. This is Anjar earthquake in the Kutch Basin, and this is the Bhuj earthquake. This one, Bhuj earthquake, and this is the 1819, 1819 Kutch earthquake, which created a something like 90-kilometer long Allah Band, or you call it, God's wall. So this is the that Allah Band is developed due to this 1819 earthquake. So this area is, of course, is zone 5, and we have experienced the long, the large earthquakes in this region. And I forgot to tell you that both the Kutch Basin and the Narmada Basin, which were developed with the plate movement by tensional regime, now generating earthquakes by reverse faulting. That means now it is under compressional stress. It developed the Reed Basin due to tensional stress, due to when the plate was moving in the geological past. Due to the internal tension, the Reed Basin was developed, and now it is under compression, and earthquakes are by compressional tectonics. So this is one beautiful picture. This is one beautiful picture that that when we came to this area for aftershock study, almost within 24 hours we reached this area. And we found that at a dung bungalow, we went for a accommodation. We found that at that bungalow, that guest house, the clock was stopped. The pendulum clock was stopped. So this has worked like a seismoscope. Means it has recorded the time. The moment the P wave has hit, the clock stopped. The pendulum stopped. So that time is recorded like this. So the past earthquake, when there was no seismometers, I think this type of thing. Worked like a seismoscope, means it had the time to note at what time this earthquake occurred, and this is one of the example how a pendulum clock can work like a seismoscope to give us the time of the earthquake occurrence. Now this is the see the damage. A well-built house, RC building collapsed, totally collapsed. And then there is total destruction of the village. The weak structure in the Bhuj area also totally collapsed. And there was some crustal upheaval. This is not surface rupture. This is just a, crustal deformation. You can say about half a kilometer long crustal deformation. And this is a liquefaction, where there was sand and loose material, and the water table was shallow, and so liquefaction was also observed here. And this was by Pandey and others, or no, this is I think natural hazard paper by Pandey. So they have shown that the maximum intensity 11 was over here, then 10, and then 9 and all. So, and it was widely felt up to say about 700 or 800 kilometers away. It was well felt. So now what is our aftershocks invasion says? Now in this earthquake also, we had something like 14 or so seismic stations, and this time we had digital seismic stations, some digital and some analog. And we did the seismic tomography. So the earthquakes are very well located, and you can see the almost two arms of the aftershocks. This is the main shock, and this is one aftershock arm, another arm like this, like a V-shaped aftershock area. And when we take a section, east to west section, it shows two arms clearly. This is the main shock at a depth of 25 km. And aftershocks, no much aftershocks at a shallower depth, all between 15 to 35 km depth, all aftershocks. And when it took the vertical sections, north-south sections, it shows nearly a vertical structure. And this is south, this is north. So nearly it's very steep or near vertical or south dipping structure, and main shock occurred here, and these are the aftershocks at a depth of say 15 to 35 km. So that was observation by from the epicenter location and from the sections. And when we plotted the number of earthquakes with depth, we found that bimodal seismicity aftershocks are maximum at a depth of say 20 to 25, and then there is some gap, and then there is some another aftershock sequence. So there is some bimodal character of aftershocks in this for this aftershock characteristics. Now when we did the fault pen solutions, we find that along this arm, the aftershocks which are well located in the month of February and in the month of March, with time and also with depth range, we have got different solutions, and they are mostly strike state solutions. And this is the main shock solution. Now you understand this is reverse faulting, and this one is this cluster which shows different types of solution, mostly thrust faulting and with some strike slip component. And this is also thrust faulting with some strike slip component. And so these arm also shows this shows different movements. Say this is right lateral movement and this is left lateral movement. So two arms of the aftershocks also shows different fault pen solutions and different movement. Since this aftershock sequence was quite huge, this is only 3 months record, and the aftershocks are still continuing. I remember Nicholas' lecture. I think this is one of the highest or largest aftershock sequence that we are recording in Bhuj area. And in Bhuj area, ISR has a special network to monitor earthquakes in this region. And I believe that still aftershocks are going for last 2 decades almost. The aftershocks still are occurring, and some few weeks back there was felt aftershocks of magnitude 5 or magnitude 5.3 or so. So this is one of the longest aftershock sequence we are recording in Bhuj, but this is only 3 months record that we made a temporary network from GSI, and with this data we did the B value mapping. That B value that is the magnitude and cumulative number of earthquakes. If you plot, you get a relation, linear relation, and that slope is known as B value, and that is the threshold magnitude, means something like 2.5 or so, or the threshold magnitude of the network, and this relation we get. So we can also use this relation in grid way, say 10 km by 10 km area, and you have some 50 events. You can evaluate its B value, and every grid you evaluate, and then you do the contouring or you do the coloring. You come out with the B value map. So that is how the B value map is produced. And you can see along this arm, as I said, there are 2 arms. Along this arm, the B value is this is high and this is low. So this way also you find that how B value characteristics is also is different for the 2 arms of the aftershock sequence. So this is another observation. Now with this section and with this fault pen solution, we tried to make a model. That was our first report in 2001 in Geological Society journal. So we found this particular section, we brought it here, and this is the main shock, and these are the aftershocks. So we know the catchmental fault over here. There is a rift basin, and the two boundary faults is this Nagarparka fault, and to the south is that Katiyar fault. So between these two boundary faults, there is a reed basin. This reed basin is existing, and in the middle of in the center of the reed basin, the fault is a gigantic fault. It's called Kachmandan fault. So this Kachmandan fault is north dipping. This is north. So this Kachmandan fault is north dipping, and this fault is not the causative fault for this earthquake. So our initial interpretation is that there could be some hidden fault. So that hidden fault which has activated at a depth of say 35 to 15 kilometer, that area we have got the aftershocks. There was no surface rupture, and there was no much activity also at a shallow depth. So some hidden fault and some some two trend of aftershocks are with the matching with the two lineaments. So then we come to this on controversy. Mondal and others from NGRI group, they also had a temporary network, and they had longer aftershock sequence recorded. And there, this is the look. As I said, the two arms of that is the aftershock locations. And this is, as I said, this is the northern boundary fault, and this is the somewhere here is the southern boundary fault, and this is the Kutch mainland fault, and this is the Kutch Reed Basin. So, seeing this visually, they presume that this boundary, this dotted line, if you can see, is the causative fault. They named it North Wagath fault. Now, this fault is not in the geological map of GSI. And as I told you, we always go in two teams, one group for aftershock investigation and one group for, isoseismal mapping, and also to see the geological fault and other things. And in Pandey 2013, we had a GSI special volume, and also in this natural hazards publications, he has not shown anything like North Wagath fault. But based on this boundary, these authors draw this North Wagath fault, and this is the North Wagath fault in the section. So this is the aftershock sections, that is main shock, and this is the aftershock sections. So they extrapolated these two North Wagath fault, that this is the causative fault for this earthquake, though there is no geological evidence of this fault. Now, S.K. Biswas, who almost spent his life here from ONGC to understand the structure over here, he shows that this is Kutch mainland fault, and there is a South Wagath fault over here, and earthquake occurs somewhere here, and this South Wagath fault is a part of Kutch mainland fault, and there is an overturn, and that fault is South Wagath fault is southly dipping southwards, and Kutch mainland fault is dipping north. And he has given a model that this is Kutch mainland fault, which is dipping to the north, and this is the South Wagath fault. This is the South Wagath fault, which is dipping to the to the south, and that at that intersection main shock occurs. And as I said, he has also shown some magmatic material which is also observed from from the tomography survey. So this is the geological model has given the South Wagath fault is the most likely causative fault, which is south dipping, and North Wagath fault, Mondal and others, they do somewhere here, North Wagath fault. But geological model shows the South Wagath fault could be the causative fault. And Pandey others did not mention anything about the North Wagath fault. So that controversy, I think, still exists, and ISR is on special investigation to resolve this controversy. And I think they are yet to take this deep seismic sounding, DSS sounding, or they have already taken. It is not yet published. So which could resolve this problem, whether North Wagath fault at all exists or not, and geological map does not show its existence. Now, I think I forgot to tell you about this. We did that. We did the local tomography as well as differential tomography. And I think I will now concentrate to differential tomography here. Now over so many years, from 2006 to 2015, this data, which is recorded by the ISR network, this data was especially, we used for differential tomography. This is published by Singh et al. I am also there. Singh et al. In BSSA in 2016. A huge data set, and this is the main shock solution, the red star, and this is the, I think, Anjar earthquake solution, and these are the aftershocks. And I will show you just tomography sections along two cross sections, that is 5 kilometers to the east and 5 kilometers from the epicenter to the west. These two cross sections are shown here. So you can see this is P wave section and this is S wave section, and this is 5 kilometers to the east and this is 5 kilometers to the west. You can see that both these sections show that Kutch mainland fault and the South Ogal fault are near vertical at depth. This is a curvilinear structure, and main shock occurred somewhere here. So the geometry of the fault is fairly identified in the tomography images, and also with these data also, which I have shown you earlier, that was our 3 months data. Now this is about some 8-9 years data. With these data also we find this is the section of the north-south section of the huge aftershocks. This is the main shock, and these are the aftershocks from depth of 15 km, 35 km, and this is South Ogat fault, and this is the North Ogat fault demarcated by Mondal and others. So we feel that South Ogat fault is vertical, and then it is taking a curvilinear structure, and that South Ogat fault is the positive fault for this earthquake, which is matching with the geological model given by Biswas and others. So this is from the recent data, you can say, and this is the section. Now, Mondal has, in his 2-3 series of papers, he has published many fault plane solutions by waveform inversion, which are from broadband data and very well constant, fault plane solutions he has published, and those fault plane solutions, the in-part fault plane we have plotted over here. Maybe something like 60-70 fault plane solutions, and we find that for 2 different periods, this is from 6 to 15, and this is another, I think, 2001 over here. I can't see, but you can see. So these fault planes, in-part fault planes, are also plotted at depth, and we can see this is very well with the South Ogat fault. And further to the north, there is a Giddy fault over here, and this is North Ogat fault, which is marked by them, and this is South. So at all our thinking, we think that this is the geometry of the South Ogat fault, which is from 15 to 35 kilometer depth, was ruptured and generated the main shock and aftershock, and that is matching with the fault plane solutions, matching with the aftershock sections, matching with the tomography images. So I think I have come to my end, and my conclusions are like this. The 1993 Kayal earthquake, the magnitude 6.3, intensity 8 and depth 7 km, is a typical SCR event, shallow SCR event. SCR means stable continental region. In Intraplate, I think this nomenclature was given by Johnston. In Intraplate, you can also, in the ocean also float, that can be Intraplate region. So to demarcate between ocean Intraplate and land Intraplate, continental Intraplate, this nomenclature was given, called SCR, stable continental region event. This occurred by reverse faulting, precise aftershock locations, seismic cross section, fault plane solutions, and seismic tomography. We did it by LET there, provide a fault interaction seismotectonic model that I have already shown you how we understand the Kayal earthquake by intersection of the two faults. The 1997 Jabalpur earthquake, the depth was 35 km. It occurred at the NSF system, that is not, Narmada South Fault system, at the crust mantle boundary of the Narmada Rift Basin. Seismic cross section and fault plane solutions reveal inversion tectonics. Inversion tectonics mean that the rift was formed by tensional stress tensional regime in the geological past. Now it is experiencing compressional stage due to collision from the Himalayan tectonics. Then the 2001 Bhuj earthquake occurred at a depth of 25 kilometers in the Karstic Basin, and it is also by inversion tectonics because it is also showing the all reverse faulting or thrust faulting. Precise locations, seismic cross section, fault plane solutions, and seismic tomography, both LET and TomoDD, reveal geometry of the fault system that caused the earthquake. So thank you so much. I'm sorry for the bit delay, but system sometimes does not obey us. So thank you all. Thank you so much for your patience hearing. Thank you.
So thank you very much for your brilliant talk on the interrupted earthquakes of India. Now, before going to question and answer session, may I request our co-session chairperson, Dr. Saurabh Barua, for his remarks. Over to Dr. Saurabh Barua.
Thank you, Shantanu. We have just heard Professor Kayal on the strong and large earthquakes. So here he has mentioned two things. First, about catalog, which we have to be to the optimum level. That means the earthquake database has to be very much elaborate and error-free. And that earthquake database is the prime input for any kind of investigation, such as seismic tomography and other specs. So in case of seismic tomography, he has touched upon that the fault interaction model that could be really understood if we understand the exact crustal velocity structure. So he has given much emphasis on seismic tomography, whether it is local earthquake tomography or inversion tomography in both ways. And apart from fault interaction model on these earthquakes, he has also posed a question through a controversy between two groups, which is still not answered. Although that answer can be the outcome of this particular workshop, the questions that has been raised through it. So on behalf of the organizer, I thank Professor Kayal such an illustrative description of all the large earthquakes that occurred in India in stable continental region to the Gujarat. Thank you, sir, for your kind interaction and deliberation. Over to Dr. Shantanu Barua.
Thank you very much, sir, for your remarks. I have seen Professor Ramesh Singh, he's online. So if you can speak something, we'll be grateful to him. Over to Professor Ramesh Singh.
Okay, thank you very much for inviting me for my comments. I really enjoyed Dr. Kayal's lecture. I always consider that he is one of the great seismologists in India. And right now, if I count, I do not find many people. We don't have many people in India who has the caliber of Dr. Kayal, and Dr. Kayal got training at New Zealand, and always I have seen that whenever the earthquake occurs, he is there. So really thanks Dr. Kayal for your nice lecture, and and I would like to say further, because I saw some of his comments about the intraplate earthquakes, and there was also question about the magnitude and then the depth. As far as I know, intraplate earthquakes in India, they, like I wrote 2-3 papers related with that. And my understanding is the Intraplate earthquake, whether Badr Salam and other earthquake occurred in the old lineaments. Okay, but the Kilari Latur earthquake, there was no existing known fault. Okay, and then the Koena, of course, we are talking about the reservoir-induced seismicity since the 1962, and we have spent so much money for the boreholes, okay, and I'm waiting yet to know about what are the findings of spending so much money about the Koena. But second, what I'm saying, the Palghar, okay, and people are working in Palghar, and we one of the papers I read, Dr. Galhout is the co-author of that paper. They are talking about the subsidences. So what I believe that in the intraplate environment, you get the magnitude of 5 or 6 earthquake, and the damage is within 10 kilometer by 10 kilometers. I have not seen earthquake of higher magnitude in the intraplate regime. And when you are talking about the Jabalpur, of course, 35 kilometer, and then the Bhuj is a different story because this is the long existing fault. So intraplate earthquake occurs when which is what we are expecting due to water injection or water withdrawal. Okay, and the Palghar is the one we are observing, and similar to this, there are earthquakes in Valsad. There are earthquakes in Sihor earlier. So these are the, of course, I also touched upon in my talk. This is the fluid induced, and in our interplate regime in the shield region, there are fluids. And if you see the statistics, and I know ISR, some colleague, they have also published papers. Whenever there is a rainfall, and then the earthquake have occurred. Okay. So we should try to see that really in the intraplate regime, if there is a rainfall, we are getting earthquake. And like Delhi is a good example. Okay, and still people are trying to reach to the cause, but they have not. I have not seen anything about this because the magnitude is 3, 3.5, 3 and 2, 2.5. The big question I want to raise is this Delhi earthquake is the reservoir-induced seismicity? So you please think over. My answer is yes. Okay. So thank you very much, and I really admire Dr. Santanu and this institute for arranging this series of lectures. Okay, and right now at my place it's midnight, but I was very much excited to listen, Dr. Kayal.
Yes.
Thank you very much.
It's midnight. Thank you, Dr. Kopra Singh. Thank you so much for saying for the kind comments, and you are really midnight. You are awake to listen to me. Thank you so much. I'm overwhelmed. Thank you so much.
Thank you.
Thank you very much, sir.
Thank you.
Now let us go for question and answer session. Mr. Prasija, over to you.
Yes, sir.
There are very important questions are there.
Okay. With your permission, sir, I'm going to read out the remaining questions. Divjyoti Goswami wants to know, are majority of the interplate earthquake in India caused due to the large differential stress or the influence of the other parameters like fluid pressure, friction, etc.? If yes, have you observed control of such parameters from seismological data?
Oh, a very expert question. Wonderful question. Yes. uh, I missed one point. One is fluid, and another one, two things he has suggested.
Friction, sir. Friction.
Any? You again read it? Question.
Okay, sir. Are the majority of the interplate earthquakes in India caused due to the large differential stress or had the
Differential
influence of-
stress. Yes. That point I forgot. Yeah. I think he has mainly asked whether due to differential stress or due to fluid population or any other so many regions. I think all are responsible. Now differential stress, I think, yeah, that is what you mean by deviatory stress, and that is the reason for generating earthquake for that particular local earthquake, because the regional stress is, say, from the Himalayan region. There is a regional stress which is, say, almost in northeast direction, and then that regional stress is causing a local deviatory stress due to your heterogeneity in the local area, say some fault zone or some other heterogeneity. So that that heterogeneity or that fault zone in the local area is experiencing some deviatory stress due to the regional stress. So you are right that it is the differential stress or the deviatory stress which is the cause of earthquake. And your other query about the fluid, fluid percolation, that is, I think, greatest example is the Koyna. Koyna is not really, if I understand reservoir seismicity, Koyna is not really generating earthquakes due to the reservoir load. It is almost negligible. It is a tectonic earthquake, and it is the fluid percolation. The reservoir water is going to the down to depth, and it is accentuating the slippage in the fault system. So yes, fluid interaction or fluid role in generating earthquakes. I think the textbook example is Koyna earthquake. And say, for example, also the Kilari earthquake, there is supposed to be a low velocity structure below the, below at about 35 or 40 kilometer depth. So that could also, percolate to the fault system, and that accentuate the triggering. So in one word, it is the fault, it is the, the fault system which is getting triggered. The first reason is that deviatory stress, and the second and or other reasons that is some fluid percolation or pore pressure increase, which also causes the triggering, like in Koyna, that is the fluid pressure is causing the, triggering the lot of earthquakes there. Yeah, I think your question is very pertinent, and I think the answer is yes.
Okay, sir. The next question is from Arpita. She wants to know where in India we can find the maximum depth of occurrence of intraplate earthquake.
Oh, that I think I mentioned, or if not categorically, now I mentioned that in the Rift Basin, like that Kutch Rift Basin and the Narmada Rift Basin, in these two Rift Basins is observed. It is quite well estimated depth, and they are of the order of, in Narmada Rift Basins of the order of 35 kilometer depth, and Kutch Rift Basin of the order of 25-26 kilometer depth. So in the Rift Basin, the earthquakes are deeper, and at the moment, these both the reed basins are generating earthquakes by inversion tectonics, that is by thrust faulting mechanism or reverse faulting mechanism. And typical shallow earthquakes is like that of Kilari, like that of Koyna, like that of Bhadrachalam or Ingol, or like that of Midnapur. They're all typical, intraplate earthquakes at a shallow depth, say 10 kilometers plus minus few kilometers. So that is the normal depth of the intraplate earthquakes, 10 or less. And deeper earthquakes is we are very well observing in the Rift Basin, as for example Narmada Rift and the Kutch Rift. These are the two active Rift Basins in our Intraplate region. Yeah, thank you so much. Good question.
Okay. So the next question is regarding the Gujarat and Jabalpur earthquakes. Bilham 2001 and 2005 science has hypothetically that these are the bending plate earthquakes. It seems fitting as well with the depth of this given earthquake and flexor effect, that is wave-like. Please comment on this, sir. How likely to happen?
It's a very another expert question. Yes, Bilham's hypothesis is that there are many hypotheses. That Bilham hypothesis, there is a flexure of the plate and that is causing the earthquakes. But again, the flexure of the plate, normally we get the flexure causes tensional regime, and if that is dominant, then we should get normal faulting earthquakes mostly. So here particularly these two Reed Basin has generated earthquakes with reverse faulting, thrust faulting mechanism, and they are, as far as our understanding goes, they are of inversion tectonics, that is due to the compression from the Himalayan region, this Reed Basin is now under compressional stress. So this is more likely causes of the earthquakes by reverse faulting, and due to the flexure of the plate, yes, he has his model and he has his argument. I appreciate that, but I'm yet to see the with fault plane solutions in this region with the flexure of the plate. If it is with the, I believe if it is with by normal faulting and strike slip faulting, or particularly by normal faulting earthquakes, then it could be solely due to the flexure of the plate. That is my understanding. But yes, that is a concept, a hypothesis. Like recently we have published a paper in Science also by Kaulakov and others. It was a Indo-Russian project, and we have observed that the Narmada Reed Basin is almost like a divider. It's in the center of the Indian plate, and northern part we known as the northern shield, and southern part is the southern shield. And in our regional tomography, we have seen that the southern part of the Indian shield is of higher velocity, and northern part is of lower velocity, means to the north of the Narmada Reed Basin, that shield area or interplate region of lower velocity, and it's most likely that the southern part is gently dipping below Narmada Reed Basin, or that boundary fault, and it could be a Himalaya-like situation in the geological time. So these are all conceptual model, and yes, they are model. I think it cannot be discarded, but yes, these are the models that we can think of different hypotheses and different thinking. Yes, that's model. I know about that. Yeah.
Yes, sir.
Next question.
The next question is, can you please highlight on earthquakes in Delhi NCR region in the last 3-4 months?
Oh well, if I remember, Delhi has produced past earthquakes. Some time back, I forgot the year. it is of magnitude 6 or so. So there is a past record of strong earthquakes, if not large earthquakes, strong earthquakes in Delhi, Delhi region. There are some, northeast trending fault zones are there. So these recent earthquakes during the last few months is not really a surprise. It is, I think, it is a lot of discussion has been made on this, has come on this. I think this is a part of Delhi fault zone activity, and why sometimes the earthquakes are more frequent and sometimes is quite. I think that is also a part of that tectonic stress accumulation and tectonic stress release system is part of that. So I think Delhi earthquakes is not surprising. It is within the normal seismicity of Delhi seismicity, and Delhi has a past. In the past it has recorded a strong earthquake. So I don't think there's any reason to be panic, but I think there is enough reason for retrofitting the buildings. We should live with the earthquakes, and we should make earthquake resilient houses to live. I think that is the lesson we should take. Yes. Next question.
The next question is, the Basin oil blowout incident has caused some earthquake. Is it true, sir? Please let us elaborately.
Very good question. Yes, I wish I could do some work here, but I'm a retired person. I can't. I don't have the infrastructure to do this. I think immediately a network of at least 10 stations should have been made around this blast region, because what happens, to my understanding, though I have not done much surface work in the oil industry, but I have done some borehole work, borehole geophysical work. Why this is a different topic you have brought into the picture. So let me share my little understanding about this. Why this such type of blow occurs? There are different reasons. Mainly is human failure, failure, machine failure, like that. The human failure is when you seal a borehole, you put the casing and then you put the cementing material to seal the reservoir formation so that the oil does not flush into the borehole. Only when you require the production, then you blast that part of the cemented portion and the oil comes to the borehole and you do the production. But there could be failure of the what do you call it, cementing material that collapsed and the oil flushed into the borehole, and tremendous pressure. With tremendous pressure, the gas has come and it has caused fire. So now your question, pertinent to your question, whether that can cause earthquake? Yes, of course that cannot cause that. I don't think it will cause a very large earthquake. If large earthquake occurs, that will be for tectonic reason, and this type of flow of oil may accentuate that. But this type of flow of oil, crude oil into the borehole or into the surroundings, with tremendous pressure, definitely makes some small tremors of the order of magnitude 2 or so, 2 and above. So actually, we monitor this type of seismicity where there is oil producing field in all developed countries, except I think here. We are not monitoring seismicity when we are producing oil or when we are doing the secondary production of the oil. So it is a must. We must have the network, and all oil companies should have the a small network to monitor, at least few stations to monitor seismicity. So I think to your question, the answer is yes. Such a flush of crude oil with generation of new fracture can cause some earthquakes. and that can be, if it is very shallow, naturally they are very shallow. The oil is at a depth of 3 kilometers or so, oil reservoir. So if they are shallow and magnitude 2, they may be felt. So yes, that flushing of oil and gas may cause some, earthquakes, and that can be felt because they are very shallow.
So we can
Next.
have last question from Navajyoti Molia.
Yeah.
Yes, sir.
Yes.
Navajyoti Molia wants to know, in between intraplate and interplate earthquake, which plays major role in evolution of Earth and why?
Which plays more resolution? What do again tell?
Which plays major role in evolution of Earth?
In between interplate and intraplate earthquake.
I think if I understand your question, you are trying to say something of the evolution of the Earth. Say evolution of the Himalaya, naturally interplate region. And in terms of the subduction region or in the collision region, the Earth is continuously deforming. So if you mean that is the evolution of the Earth, means Earth changes, is locally it changes the height or elevation or whatever way you want to say. Yes, it is the interplate region where there is direct interaction between the plates. That part is more vulnerable for deformation, and compared to the intraplate region. Yes.
Thank you very much, sir, for this nice interactive session. Now, may I request Mr. Gautam, Dr. Gautam, for vote of thanks. Over to Dr. Gautam.
Thank you very much. I am being privileged on being asked to offer the vote of thanks for this occasion. Thank you, sir. I offer my sincere sense of gratitude to Professor J.R. Kayal, sir, for being with us in today's lecture and showering us with immense knowledge on the interplate earthquakes and the mechanism behind them. Thank you, sir. I want to thank Dr. Saurabh Borua, Chief Scientist, Session NIST, for chairing the session and showering us with the comments and valuable opinions on this study. I also would like to thank Professor Ramesh Singh from Chapman University for being with us during the event. Thank you, sir. Thank you very much, Dr. Santanu Borua, sir, for organizing this event and creating such a knowledge-sharing base for the whole geoscience fraternity. Thanks goes to the whole organizing committee and the supporting staffs for being 24/7 during the event. And also last but not the least, thanks goes to the participants for participating during the event and make it a big success. Thank you very much.
Thank you all. I got this opportunity, and thank you all for